All right, our next speaker for the session is Kacper Debski from the University of Warsaw. He's going to talk about quantum time dilation in a gravitational field. Kacper, wherever you want, the floor is yours.
Thank you very much for the introduction. Today I will talk about so-called quantum time dilation in a gravitational field. My presentation is based on a paper that is not yet published, but it's available on arXiv. So if you are interested in this topic, you can easily find it in the internet. In my presentation, I will introduce the general idea of quantum time dilation, and then I will show you our extension of this general scheme to the case of an atom placed in the gravitational field. I will also describe the model and then show the result of our calculations. So let's begin with the physical background of our considerations. Based on special relativity, we know that a moving clock reaches a time that depends on its velocity, and it's called time dilation. The same effect appears when a clock is placed in a gravitational field, and then such a case it's called gravitational time dilation. At the same time, on the opposite side of physics, we have quantum mechanics, a theory that allows us to construct a state that has two contradicting properties at the same time, like a famous Schrödinger cat that is dead and alive at the same time. And it's natural to combine these two theories and find what happens with a quantum clock experiencing time dilation. What happens if a clock will move with two velocities at the same time, or in a gravitational case, if it will place at two heights above the Earth, or truly speaking, if its state will be given as a quantum superposition of these two heights. Now I would like to briefly summarize you an idea of quantum time dilation introduced by Alex Smith and Mehdi Hammadi several years ago. They started from an idealized model of a clock that is a particle with some internal degrees of freedom that serve as a clock. And then they define the time operator in such a way as an operator that that commutator with Hamiltonian is given by I. And then they found that for an atom prepared in the superposition of two Gaussians, describing the distribution of momentum, they can calculate an average time measured by such a clock. And here we can see a definition of a state psi p1 and psi p2 as a Gaussian centered around some momenta p1 or p2. The final result of their calculations can be written as this kind of expression, and it means that average time measured by a clock when the laboratory clock shows time t has two contributions. First of all, we have a classical one that is just a normal averaging of two time dilations corresponding to two Gaussians. And the second one, the so-called quantum time dilation, that is a consequence of a quantumness of the initial state. The presence of the second quantum term in the average time is exactly what we will call quantum time dilation. Some time ago, we also, together with Alex Smith, Piotr Grochowski, and Andrzej Dragan, we also found what happens to a more realistic model of an atom experiencing kinematical time dilation. And we found that this result is not only the hypothetical consequence of time operator, but it seems to be a universal property of the time itself. And our result of gamma q was the same. It convinced us to analyze the properties of a clock experiencing now gravitational time dilation. So let's go to the details of our paper. Knowing all the things I have just shown you, we can analyze the properties of quantum time dilation for a gravitational field. First, I will tell you about the construction of the clock, and then I will show you how to apply this model to measure a time. In our work, we used a more realistic model because we used a two-level atom interacting with the quantized electromagnetic field. However, we didn't use a Schwarzschild metric to describe gravitational field, but based on the equivalence principle, we placed our model in a Rindler spacetime. So in other words, instead of atom placed at two heights, we analyze the properties of an atom moving with two accelerations, having the same event horizon. Before we start, let us focus on the form of the Hamiltonian, describing the system without any kind of gravity or any acceleration. So please note that the zero in the bracket in the superscript means that we don't have gravity in this level. The total Hamiltonian consists of three terms: Hamiltonian of the atom, electromagnetic field, and the interaction between them. I mean, atom and the field. And the model of an atom is, in our case, the two-level system with the energy gap capital omega. And the Hamiltonian of the field is just the standard formula for a quantized electromagnetic field with some frequencies omega and creation and annihilation operators A. We also have dipole interaction that has the following form, and it means that the energy of the interaction depends only on the electric field outside the atom. Now I suppose we are ready to discuss the role of the gravity, I mean acceleration in our case. We can show that an atom placed in a spacetime with some G00 component of a metric has the energy that is just modified by square root of this parameter G00. And according to this, we can write our Hamiltonian in the following way. And here we use the exact form of a Rindler metric, and here function phi in this formula is a linear gravitational potential as a function of z, that is the height above the reference hyperbola from the Rindler metric. Other terms from the Hamiltonian will be also modified by appropriate quantization. So we will use electromagnetic field quantized in the Rindler spacetime. And for example, instead of operator A, we will get some operator B that creates the field inside the Rindler wedge. Now, the total Hamiltonian that we described already will be used to find an evolution of the system that consists of an atom and the electromagnetic field. So let us write the initial state of the whole system in this way. And here, this function, sorry, it should be alpha, but it's psi. So this function psi is a function, is a probability amplitude that measure the probability that that excited atom is placed in the vacuum exactly in the position z. So in this notation, the first position in bra describes the position above the reference hyperbola, and the second corresponds to internal degrees of freedom, and the last one is the state of the field outside the atom. And then after coordinate time tau, the state can be written as this. And now alpha is also a function of time because everything changes with time. We also have the second term proportional to this coefficient beta that measures the probability that atom has decay and emits some photon of a momentum k and polarization lambda. And in our paper, we carefully derive these two functions. But the most important fact is that we can find the probability that atom stays in the excited state until coordinate time tau. And this function has the form of exponential decay, so we can differentiate it and find the transition rate that will describe how the state of an atom changes with time. And the inverse of this quantity will show the average lifetime of the excited state, so it can serve as some kind of clock in our model. Now I suppose we have every tool needed to finalize our calculations.
2 minutes.
So we can find the total transition rate for two cases: for the state when the state is prepared as a quantum superposition of two Gaussians, or a classical mixture of them, and then compare one with each other by this kind of formula. And what is interesting, that the result that we obtain in this way is written here, and as you can see, this result is very similar to Okay, so it's just, I would like to finish that this result shows that we have the same, or strictly speaking, the very similar form of quantum time dilation. So it seems that that this effect could be really universal, and it does not depend on the details of the considered model. Thank you very much.
Thank you, Kacper.